Hello there, peoples! Translating velocity versus time graphs 2. So this is a little more sophisticated than before, but we can handle this. Here we have 3 phases of motion, 0 to 5 seconds, 5 to 10, and 10 to 15 seconds. From 0 to 5 seconds, we have a change in velocity of 10 to 20 meters per second. Notice the axis over here. Then the object that is moving maintains a velocity of 20 meters per second. It is constant. And then it actually changes, it slows down until stopping, and then it actually goes a bit in the negative direction, okay? So in order to translate this into a position versus time graph, we use the same techniques as we had before, which is to take the area bounded by the velocity versus time graph. So here I've laid them out for you, and you can verify my work. 50 meters, 25 meters, 50 meters, 50 meters. This triangle here is 25. And this, though, because it's below the 0 line here in this 0 axis of velocity versus time, it's actually a negative area, meaning that there's negative displacement and we're moving backwards. So translate it here, what I've done is dotted each of the spots. 75 meters is as far as we go from 0 to 5 seconds. Then we go 100, so we're at 175. And then we go 25 more, which is this triangle, up to 200. And then because of this negative area, negative 25 meters, we'll go backwards 25 meters. This is, again, the area represents displacement from previous position. So the next thing, though, is to figure out, well, how is this going to look? How am I going to connect the dots? It's not enough to just draw lines like a constellation. That doesn't work. And the reason is, with the changing velocity in position versus time, we have a changing slope. All right, as we get faster, the slope gets steeper. So actually from 0 to 5 seconds, even though we start here with an initial velocity of V0 of 10 meters per second, this indicates that we're going to actually increase our velocity, so the slope gets bigger. And so it actually is a bit curved, so it looks like this. So it's not a straight line, but it actually curves upwards, so the slope gets steeper and steeper. From 5 to 10 seconds, it's a constant velocity. Constant velocity means the slope is constant too. So this is just a straight line. This one we can just connect straight like that. That's not supposed to be curved. That's just my artwork here. This is definitely curved. All right, so I'll write that down. Curve, curve, and this is straight. And now here we have what's called a negative acceleration. Our change in velocity is negative because of this slope here. So what does that mean? We'll discuss in further detail when we create acceleration versus time. That's coming up in just a moment. But one thing we know is that we're going to be slowing down. And if we're slowing down, we're changing our velocity. So the slope is going to be changing, but it goes towards 0. So actually the slope, rather than getting steeper, gets flatter towards 0. So this comes here and curves and gets completely flat here, flat, like so, at 200 meters. All right? And it's doing the same thing in reverse. We're gaining velocity, but in the negative direction. So it's going to be curved, but in such a way that the slope gets steeper, but in a negative direction. Okay, so now we have the same curve like this, but you notice how the slope is getting steeper, but in a downward direction. And that's how it works. So we're using the same skills that we had before, just applying it in a more refined way with a slightly more complex situation. What I would like to introduce to you also is something slightly new, but very doable. It's called acceleration versus time. Hey there, Papolas! Velocity versus time 2. We're going to look at another feature. Now we're going to look at the slope and see what that gets us. Slope seems to be something that gives us some interesting information. It will here too. So if we look at the equations that describe the motion of each of these phases here, they are, well, lines. So y equals mx plus b is the standard mathematical form, but we can do a little bit better. From t 0 to 5 seconds, time is the interval of 0 to 5 seconds, we got v1 equals m1t plus v0. Okay, the m is more of a generic slope, but we're going to derive some meaning from it soon. And v0, as we see here, is the y-intercept. It represents the original velocity of the moving object. If we were to extrapolate these things back to the vertical axis, each of them would have a different intercept, of course. But because they're stacked together as motions, we're not fully concerned about it except for this guy over here. There's the piece of information that is really important though for every one of these, and that's slope. So check it out, the slope of the v versus t graph, rise over run. We go rise meters per second, the velocity. We go run seconds. So what we have here is meters per second per second. That's the rise over run, which should sound familiar, right? It's meters per second squared. This is average acceleration. We can derive acceleration information from this graph, okay? Very similar to what we did before with position versus time and the slope of that becoming the change in velocity. So we have gone slightly deeper into the rabbit hole. That's kind of what it is. This is just one step deeper in terms of the information. This is as far as we go into the rabbit hole, pretty much. And it's constant acceleration that we will deal with. Very rarely would we have a changing acceleration. If you do, and if you even take a slope of the graph that we'll take over here, that would be something called the jerk. So in motion, we know we can change our velocity and gain speed, but if you do that in a jerky way, that's kind of, someone named it before, then that's called the jerk, and there are a few levels below that. That's used mostly in automobile and aeronautical engineering, then have to worry about the herky-jerkiness of the ride and stuff. So, but this is as far as we go down the rabbit hole. So what we can develop here is an acceleration versus time graph. We can represent the information in the form of acceleration versus time, and it's almost perfect. It does lose a little information, and I'll get into why in just a moment. Okay, so the slope, here we go. This cute guy over here looks familiar in format, right? We have average acceleration is the change in velocity over change in time. V minus V naught over T minus T naught. Hey, that format is just the same. We've seen the one before regarding position and velocity, right? So patterns, guys. We're seeing some patterns to develop. Okay, so what's the slope from the first interval? Well, from 0 to 5 seconds here, 20 minus 10 over 5, 2 meters per second squared. So I would represent this slope here as acceleration. It's the change in velocity, and that's 2 meters per second squared. 0 meters per second squared because there's no change in velocity from 5 to 10 seconds. It stays at 20 meters per second. And here we have a giant negative slope, negative 8 meters per second squared. So in our case, we saw this means that we're going to be slowing down to 0 and then speeding up but in a negative direction. You're going to be seeing this in a simulation really soon. All right, so this is acceleration versus time. It's really nice, but from acceleration versus time to velocity versus time, or velocity versus time to position versus time, there can be some loss of information. For example, the area here is, if we took the area, that would give us the change in velocity. And that area here is 10 meters per second. So 2 meters per second times 5 seconds. And that represents the change here. Coincidentally, this starts at 10, but we have no knowledge though of our starting velocity. This graph doesn't tell us that. We would have to have additional information from somewhere else. Just like if we were to not start at the origin, if we were to start a displacement somewhere or position somewhere else, then the velocity versus time graph wouldn't tell us about that. So we get, some information about it. We have, in this case here, 5 times 8. So we get the change though in velocity. So we notice that this change is 40, and that's what tells us. This tells us over here the change is negative 40 meters per second. Okay, so we can go back from this graph to this one. The key is though that it won't tell us if we have an initial velocity. That's additional information, and so that's somewhat interesting that it's information that's kind of lost. It's not encoded in this particular graph, and that's what it is. Beautiful stuff down the rabbit hole. Okay, Morad out.